So good morning, everybody, and welcome to day one of Chemistry 104. So right now we are going to go over the concepts of the introduction to chemistry, and we're going to move on to talk about chapter 2. Let's get started. The first thing that we are going to talk about is what is the definition of chemistry. As you can see, chemistry is defined as the study of the composition, structure, properties, and reactions of matter. Okay, matter are going to be all the substances that are around us. Okay, and those substances is what make up the world. Whenever we think about chemistry, sometimes we think about, shows that have popularized chemistry, like Breaking Bad. Put a 1 in the chat if you have heard of Breaking Bad before. There you go. Some of you have heard about Breaking Bad. But understand that in chemistry, Breaking Bad, in other words, synthesizing illegal drugs is not the only thing that we have as chemists. All of us can have chemical knowledge in order to understand the world around us. So for example, the second image that you see here in the slides, it is actually the firework display that is, I think this is Disneyland, not Disney World, but as you can see, there's the castle right there. So those fireworks and the colors that you see there, and soon, in about a few weeks, we're going to be participating in, for those of you that want to see it, the fireworks at 4th of July. Understand that the colors in the fireworks actually comes from ions, and we're going to learn about ions in this class. So the different elements in the periodic table form charged species that are called ions, and that's what gives the different colors for the fireworks. So you can see actually elements at work when we see firework display. Other places where we know that they're chemicals, and sometimes we don't even think about them, is in food. So in order to energize our body, we need to consume fruit, vegetables, bread, so on and so forth, as you can see in the third image. All of those, when our body looks at it, it looks at it at the molecular level. It looks at the elements that came together to actually make those compounds, and it utilizes them in order to create energy in the body. Now, it is important that you guys are here and you are able to study chemistry, because you can see that we have different chemicals and structures out there. And in the bottom, okay, of what you see here in the structure, we have 3 different structures. So right now, maybe some of you have seen chemical compounds before, maybe you have seen organic compounds, but when we look at them, at first, we cannot really tell what they do and, what they are, okay? Now, just taking a wild guess, let me just see. If I label these compounds A, B, and C, okay? And this is why it's important that we are learning in this class. Let's put in the chat which one of these 3 compounds you think it is the most dangerous, just by looking at these structures. That right now, it doesn't mean anything to you guys, but as we progress in this course, you are going to learn more about them. Let me see, I see some A's, I see some B's. Again, this is just based on you guys looking at the molecules and seeing what they are, okay? Which one is the most dangerous? I see that, people, when it comes to this, it's all over the place. This is why you guys are here. So you're able to actually distinguish between these 3 molecules. Let me introduce them to you. The first molecule, which in terms of size, it doesn't have as many atoms as, for example, the second one. The first molecule that you have here, this is crystal meth. Okay, this is an illegal drug that causes addiction, and it is sometimes made in households. Anyways, super bad. The second one, molecule B, this is caffeine. Maybe some of you have coffee this morning. So what your body identified and what gave that alertness to your brain was that molecule that is in the middle. Now, molecule C, for those of you that take vitamins, this is vitamin C. Okay, so if you drink juice in the morning, if you consume citrus fruits, this is actually vitamin C. Okay, so as you can see, it is important that in this course we learn about chemicals, we learn structures, because at glance, when we look at molecules, we cannot even tell what they are. This is why we are here, and we're going to learn many molecules, and we're going to see their properties, and we're going to see some applications of them. Now, since now I introduced the concept of chemistry to you guys, let's now move on to chapter 2, where we are going to learn about what are measurements. When it comes to a measurement, understand that the definition of a measurement is that it's a definite magnitude of quantity, capacity, or dimension that is adopted by convention or by law. When it comes to measurements in the scientific world, we typically use the metric system of measurements, or at times there is a modification to the metric system that is known as the International System of Units, and it's another standard that is used worldwide. Now, you can see here that in table 2.1, we have a selected number of measurements and their abbreviations. We can see that we have the measurement of length, volume, mass, temperature, time. We can even know the amount of molecules. We can know the amount of radiation, just to name others. In table 2.1, you can see that we have the abbreviation for the metric system and also the SI system, and what are the units of measurement. So one of the things that you guys are going to notice is that whenever I'm lecturing, if there is a table that is in the slides and also in the textbook that it is going to be used for the exams, I will label it. So table 2.1, use for exam 1. What that means is that there's going to be questions in exam 1 based on this table. Taking that into consideration, as you can see on the right side of the slide, we have an image of some people just eating brunch. Okay? By looking at this image, and also taking into consideration that I introduced to you guys some units of measurements, which ones can we say are actually shown in that image? Let's make a list. Let's put it in the chat. Great. I see volume. So Geraldine, in terms of volume of what? I see length. There you go, the grams of the appetizers. Great job. We see grams. So give me the examples. Where do you, great answers. I see that people are putting mass, but in what concept, or how do we see the length of the table? Thank you, Jessica. Let me just put some here. The length of the table. I saw that some people put volume. The volume of what? The mass of the cup. Great job. In the cup of coffee that is here. The volume of the tea. Great job. This is just to name a few. So as you guys can see here, when we're living our lives, we're still, exploring concepts that have chemical bases, okay? And units of measurements is something that we do in everyday life. From when you pour your juice, your water, your coffee in the morning, to how much water is spent at home when you are cleaning up or taking a shower. So understand that units of measurements are all around us. Now, when it comes to units of measurements, and give me a moment because there is a delay. Oh, great one, the mass of a baking soda, time of day. Yeah, that's a good one too. There you go. So when it comes to measurements, understand that we are going to define what is a measured number. And possibly some of you already know how to do measurements, okay? Specifically of length and volume. But here I'm going to explain how do we obtain measured numbers and what are significant figures. Let's get started with defining what is a measured number. So measured numbers are the ones, again, that is very logical, that are obtained when you measure a quantity. Now, it is important to note that when we write a measured number, there are particular things that need to be included in that measurement. And we can see that when we write a measured number, we are going to have a particular standard that we're going to use to give us our measurements. In the case of the example that we have here, we have a ruler and we're measuring this object, which happens to be a pencil. So when we have a measured number, first we're going to have numerical values that are given by the marked lines in our instrument of measurements, okay? So we can see here that in this instrument, we have centimeters, and we can see that we have numbers from 0 all the way through 17. So that means that this instrument can only measure something up to 17 centimeters. Now, when we look at the marked lines, at the marked values, and let me just zoom in. Let me just do a dotted line of where this is at, okay? Based on the observed numerical values, we can see that this object is at least 10 centimeters because the observed numerical values tell me that this object is 10 centimeters. But understand that we need to include an estimated value because we see that this object is past 10. It's not quite 11, okay? So we are going to create an estimated value based on what we think that is going to be between 10 and 11. So this estimated value, basically we do it by taking between the numbers of 10 and 11 and in our heads creating 10 lines, okay? So when it comes to the estimated value, again, this is an estimate, okay? So let's say that I look at this and I'm like, this looks like 10.8 because this is the estimated value, centimeters. There may be some of you that say, you know what, Dr. Luz, I think that this is 10.9 centimeters, okay? And guess what, you guys? We are both correct because that last digit is going to be an estimated digit, okay? Now, that estimated digit, you have to estimate correctly because by looking at this object in our ruler, we cannot estimate that is 0.4 because it's more than halfway between 10 and 11, okay? Now, remember that this last number is always necessary, okay? That estimated digit. And then lastly, when we have a measured number, we need to include the unit. So again, when we have a measured number, we need 3 components. Based on our instrument, we need the observed value from marked lines. We need an estimated value. And we need the unit of measurement. Now, let's actually move on and look at examples of utilizing different instruments and how we are going to report those measured numbers differently depending on the instrument that we have. So let's actually look at these two rulers, okay? These two rulers measure about 20 centimeters, as you can see here. In the image that we have here, we are going to measure the length of this rod, okay? Let me just do a dotted line so we can see where this lands, okay? Now, if I'm using the instrument on the top, and I want you guys to put it in the chat, what's going to be my measured number utilizing the top ruler? What could be a measurement? What is my measured number? I see a lot of 9 centimeters, but we're missing the estimated digit, you guys. Because as you can see here, this is not quite exactly at 9. This is past 9. Excellent. I see that some people put 9.3, 9.4. I agree with that. So utilizing that top ruler, I can say that this object is going to be 9.3 centimeters or 9.4 centimeters, right? Because again, we can see that this ruler on the top, okay, is going to measure at least 9, but then this object is a little bit past 9. So that's why the 0.3 or 0.4 is going to be our estimated digit. Our unit is going to be centimeters. But let's now see if we have different markings, meaning the ruler that we have in the bottom. The ruler that we have in the bottom actually, and let me just zoom in so you guys can see it more closely, has markings, okay, for specifically that 0.3, 0.4. So for the ruler in the bottom, we are going to have different, we're going to report measurements a little bit differently because our known values based on the marked lines is different. Oh, I can see already some people are putting in the chat, great. So based on the line that I did, and again, this is just a line that I drew, we can see that this object, specifically on the ruler on the bottom, it looks like it lands on the line of 9.4. Let me zoom in so you guys see that. Some of you may be like, it's not quite there. It could be the 4, okay? So here, if you see it exactly at 9.4, then you can say, okay, my known digits are going to be 9.4. Now, if you see it exactly at 9.4, then your estimated digit is going to be 0. Maybe you'll be like, you know what, Dr. Luz, I think that this is going to be a little bit before that 9.4. And you may say that this is going to be 9.39 centimeters. So understand that the ruler in the bottom, because the markings are different, there is actually a marked line for that first decimal place. Those are the known digits in this instrument. And then after your known digits, you need to put the estimated digit, okay? Any questions when it comes to a measured number? How we report them? Go ahead, Victoria.
You answered my question.
Oh, okay, no problem. Let's
Thank
practice
you.
now,
Thank
you
you.
guys.
Excuse me.
Oh.
Oh, I gotta put, sorry. I
You're
gotta put
good.
my hand down. Oh, how do I do that?
If you go back into where you raised it, like it actually tells you. There you go. Great job.
Sorry.
No problem.
Like, Jesus.
This is a learning process. Okay, I'm going to give you guys a minute to tell me. Oh, there you go. Now it's here. What will be the measurement with the ruler on the top versus the ruler on the bottom for this paper clip? So we're going to propose, and your answers, you guys can separate it by a comma. Let me do the dotted lines. Understand that when it comes to this, the dotted line, I actually don't put, if you look at the chapter 2 homework, I don't put the dotted line. Give me a few moments because there's a delay in my markings. There's a little bit of a delay in my markings. There you go. Now I see them. Okay, so for those of you, let me go back into the chat. For those of you that put for the top one, 5.9, 5.8, that's a good answer. So 5.8 centimeters or 5.9 centimeters. I will go with 5.9 because it looks very close to 6. Okay. At least my preference will be this one. But understand that this is an estimate. So when it comes to this and you're answering it in the chapter quizzes, understand that I take into account the estimated digit, but you have to estimate the correct way, you guys, though. You cannot say that this is 5.1. Now, when it comes to the bottom ruler, we can see that this is at 5.9, so we can say 5.89 or we can say 5.90. So for the bottom ruler, we need 2 decimal places. And remember that the reason why we need 2 decimal places is because the bottom ruler has markings. The known values for that first decimal place are given. Okay, so for those of you that answer 5.89 centimeters or 5.90 centimeters, or even if you decide 5.91 centimeters, those are all correct. Just because, again, given the bottom ruler, we need 2 decimal places because the known digits are the whole number in the first decimal place. Any questions? For how to measure length given different instruments. Great job participating on the chat, you guys. Excellent. Since there are no questions, let's move on to another measurement in which we have to take into consideration these concepts. And that is when we are measuring volume. So even though we are participating in this class virtually, understand that sometimes you may have to look at images of how volume measurements are taken. And one of the things is that typically in a chemistry laboratory, we utilize different instruments in order to measure volume. You're going to learn in lab 1 how we have graduated cylinders, we have pipettes, we have volumetric flasks, we have beakers, and some are better than others at measuring volume. But typically, whenever we have a substance placed in one of these instruments to measure volume, they actually create a curvature. And that curvature that it is created by the interaction of that substance with the walls of the container is what's known as the meniscus. So let me just write the definition of the meniscus here. Is a curvature created by the interaction of the substance with the walls of the container. The reason why I define it as just the curvature is because this curvature can be pointing down, which means that it is concave, or it could be convex, which means that that curvature is going to be pointing up. Most substances make that concave curvature, meaning the one pointing down. So whenever we're reading volume in an instrument, in our curvature, as you can see, the curve is pointing down, then in order to accurately measure that volume, we need to look at the bottom of the curvature, okay? So for example, here we have on the right side of the slide, this is going to be just an example. This is just, to be honest with you guys, this is a pipette with water, okay? And when water is actually interacting with glass, it makes this curvature. Now, when we are measuring the volume of how much water do we really have in this pipette, we need to focus on here. Oh, it's hard to see the line. Let me choose a different color. Let me use a red one. So we need to look specifically here. That's the bottom of my curvature, okay? So if I see that this instrument measures in milliliters, because we're measuring volume, okay? When I determine how much volume do I have in this particular instrument, I'm going to say, when I look specifically at this instrument, let's notice how the units of measurement are in the markings. We're going from 6 to 8. So that means that specifically, and let me just write it in the corner, if this is 6 milliliters, then this is 7 milliliters. And every single one of these markings, okay, is going to be 0.2. There is a delay. Give me a moment until the 7 shows up. Let me just write it right here. Sometimes those delays happen. This is all technology, so I apologize for the delay, but it's about to be there. So if we look again at the instrument, we see that we go from 6, then we go 6.2, 6.4, 6.6, 6.8, and then we have 7. Give me a moment, you guys. I'm going to stop sharing and resharing my slide. So hopefully the markings will show up and you guys can follow along. Excellent. Now we can see the markings. So as you guys can see here, when it comes to the markings that we have in this pipette, these lines are going to be 6.20, 6.40, 6.60, 6.80, up to 7. And then 7.20, 7.40. So when we're looking at the measurement of volume in this pipette that contains water, the same principles that we just studied in the previous slide are going to apply. So right now in the chat, what would you say is the volume of this water in this pipette? Look at where it's at, you guys. Excellent. I like what I see. Is going to be 6.6 is going to be the known digits. And then it could be 6.62. Excellent. It could be, 6.61, 6.63. So when it comes to this, again, our gap between 6.60 and 6.8 is going to be a little bit tight. So understand that here there's going to be many answers. So when it comes to this and measuring volume, we're going to do the best we can with the estimate that we have. So let's just say that this measurement .64 milliliters or 6.63 milliliters. Again, I'm just going to make you guys aware of this, okay? Excellent. I see some people saying 6.62, 6.60, because when it comes to these measurements, remember that it is important to know what are your known digits and what is your estimated digit. And in measurements, we always have a known digit and we always have an estimated digit. This is one of the reasons why measurements are not exact, because they always have an estimated digit, okay? The only time where you could claim that they're exact is it depends on the instrument. But when we're measuring length, when we're measuring volume, we're always going to have that estimated digit. Any questions on how to measure volume or length? Great. So length and volume is not the only type of measurement that we take in chemistry. There are other types of laboratory instruments that we utilize, okay? And depending on the laboratory instrument that we have, let me just stop here. There's a question in the chat. When we measure. So when you look at quiz number 2, there is a question on writing a measurement. And the directions tell you that you need to put in the measurement that you see. You have to pay attention to your object. You need to be paying attention to your instrument that you're measuring with. That being said, for the final answer, you need to enter only the digits. You don't have to put the unit of measurement, because what we're trying to do there is just to put the digits that you see based on the instrument. So make sure that you check that in the chapter quiz. There is a question about that. So going back to the concept of instruments in the laboratory. So again, measuring length, measuring volume is one of the many things that we do in the laboratory. Now, sometimes we have different instruments that do the same job, okay? So you guys can see here that we have 2 instruments to measure the mass of an object. Here we have two balances. The one on the left is an analytical balance. The one on the right is a top loading balance. Now, even though these two instruments are different in terms of their job, they do the same activity, which is measure mass. Now, the one on the left, you guys can see in the screen that is measuring the same object that we have on the one on the right. So at times in the laboratory, we have standards for mass, and this standard for mass is for 50 grams. If we look at the top loading balance, you can see that it says 50.0. Let me just zoom in so you guys can see it. So you can say, oh, yes, this is 50.0 grams. But what if we utilize a different instrument that also measures mass, but in the screen is actually giving me more digits? So if we take the same object, but then we put it in an analytical balance, we can see that the mass of that object is actually 49.9988 grams, okay? So it's not that the object, okay, that standard has changed. The difference between an analytical balance and a top loading balance is that the screen gives us different numbers, okay? Why is that? Because in the laboratory, instruments have different resolutions, okay? As you can see, a resolution is defined as the quality to which an instrument can be read. The analytical balance, the image that you see on the left, can read more. It gives me in the screen more digits. The instrument on the right gives me less digits. It doesn't make the instrument on the right or the left more accurate or so on and so forth, because that is a different activity in terms of measuring precision and accuracy. What I'm trying to illustrate here is just that resolution is different in different instruments. In taking that into consideration, this is why in chemistry, in physics, and other subjects, we have what is called significant figures. Because a significant figure is simply the measured numbers, okay? The digits that are going to carry meaning, okay, in a measurement. And significant figures is always attached to the resolution of your instrument. So if I'm comparing these two objects, then an analytical balance has a better resolution than a top loading balance. They both do their job. But we can agree that because I have more digits in the screen, in the analytical balance, it has a better resolution compared to the top loading balance. So let me just write the note here. The analytical balance has a better resolution compared to a top loading balance, just because I see much more digits in the screen. This is giving me a measured number with more digits, and all of those digits carry meaning, okay? So understand that this takes us to understand what are significant figures and how we determine if I'm given a measurement, what are the numbers that are significant in that measurement. So in table 2.2, we have a summary of how do you determine if you have a measurement, how many significant figures are in those measured numbers. So when it comes to exam 1, you need to know the rules for exam 1. Okay, and they're summarized in this table, 2.2. Now, at first, I'm going to discuss how do we know which numbers are significant. Now, I want to get you guys out of the habit of thinking significant means important. No, 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 no. Significant in chemistry just means which values are going to have a specific meaning in a measurement. Don't think that significant mean important. That is not true, at least for the concepts in chemistry. So let's first learn, how do we know which numbers carry meaning in a measurement, okay? So if we look at rule 1A, it says, a number is significant if it's not a zero. So that's what we know in chemistry as non-zero digits. So any measurement, okay, where you have in all of the digits that you see in the measurement, digits that are not zero, all of them carry meaning. So you can see here in the measurement 4.5 that has 2 sig figs. 122.35 meters that has 5 sig figs, okay? Then we have to deal with the zeros, okay? Because the zeros are the ones that are a little bit more confusing at times. So when is a zero significant? Well, as you can see in rule 1B, a zero is going to be significant if it's in between 2 non-zero digits. So you can see in the measurement 205 meters, there's 3 sig figs because that zero is in between non-zero digits. In the measurement 5.008 kilograms, you can see that that has 4 significant figures because the zeros are between non-zero digits, okay? Now, rule 1C, it says a zero at the end of a decimal, okay, is significant. I want to add a little bit more meat to this rule. A zero at the end of a decimal is significant, but there's a few things. These 2 parameters need to be met. The decimal must be written. And the other parameter is that the zero needs to be after a non-zero digit. In order for rule 1C to be true, you need to meet those 2 parameters. So you can see that the measurement 50 decimal place, okay, liters has 2 sig figs because the zero is after a non-zero digit, so it's after the 5, and there is a decimal place written. Just in case if you guys didn't hear me well, because the internet connection was a little bit unstable, let me restate that. In order for rule 1C to be true, we need to meet those 2 parameters that I wrote in. Your zero must be after a non-zero digit, and you need to have a written decimal place. So if we look at the measurement, 50 decimal place liters, that is 2 sig figs. If we look at the measurement 25.0 degrees Celsius, that has 3 sig figs. If we look at the measurement 16.00 grams, that has 4 sig figs. Remember, all of these, what we're trying to do with the sig figs is determine what are going to be the digits that carry meaning in a measurement. Lastly, we are soon going to learn about scientific notation, which is a notation that we utilize in science for writing really large numbers or small numbers. Just note that whenever you have a coefficient, which is the first part before the times 10 to whatever power you have, that the digit before the times 10, that's what's going to carry, okay, the significant figures in your measurements. Any questions so far on how do we determine what is a significant figure? So the measurement 16.00 grams is 4 sig figs because those zeros after the 1 and the 6, okay, are after the non-zero digits and they're after the written decimal place. So remember, those two rules, the two parameters that I wrote in for rule 1C must be met in order for a 0 at the end of a decimal place to be written. Because I don't want you guys to confuse rule 1C with rule 2B, which is the ones that we're going to go through right now. So let's take into account now, when is it that the zeros are not carrying meaning to my measurement, okay? So the zeros are not significant in two instances. Number one, at the beginning of a decimal number. I want you guys to pay close attention to what I said in rule 1C compared to 2A. All the zeros on rule 2A, understand that they're before the non-zero digit. They're before the 4. So they don't carry meaning other than saying, oh, this is a very small number. So that's why in the measurement, point or 0.0004, there's only 1 sig fig, because what these zeros are doing, let me just zoom in. Give me a moment, because I don't see the screen zooming in. Excellent, now it did. So these zeros right here, they're just what we call placeholders. When it comes to placeholders, they're just telling you if something is very, very small or something is very, very large. In the case of rule 2A, those zeros at the beginning of the decimal number, they're before the non-zero digit. That's why they're placeholders. So let me write that note. They're placeholder because they are in front of the first non-zero digit. Okay, so they are just telling me that's a small number. So that's why that value, 0.004 seconds, is only 1 sig fig. Similarly, in the measurement, 0.075 centimeters, only 2 sig figs, because again, those zeros before the 7 and the 5 are just telling you that those are small measurements. Similarly, in rule 2B, those zeros are also placeholders. The reason why they're placeholders is because they're just trailing, they're after non-zero digits. So for example, in the first measurement, it says 850,000 meters. That is only 2 sig figs, because the role of those zeros basically is to tell you that we have a very large number. In the value 1,250,000 grams, again, 3 sig figs. Just because what we can see here is that those zeros are placeholders for a large number. So again, in rule 2A, this is going to be for small numbers. They're less than 1. So that's why they are placeholders. And those zeros are just telling you that we have a small number. And similarly, if we have, for example, a very large number, those zeros are also placeholders, okay? So in order for us to solidify this concept of sig figs, let's actually do some practice. Let me just take an image. Let me just paste it here. Because we just studied this concept. Make sure that the rules are here for you guys. I already had them in here, but I want them to be here with my notes. Excellent. So this is with the notes that we just took, okay? So I want you guys in the chat to tell me how many significant figures we have in the different measured values, okay? Based on the rules. I will be making notes going along, okay? But I want you guys to participate. So when we look at the first measured value, okay? How many sig figs in it? Let's put it in the chat. Excellent job. So it's going to be 1 sig fig. So the significant figure shorthand that I utilize is usually SF. Or sometimes I write sig figs. Okay, just understand that's how I do it. So which rule tells me that this is the reason? This is rule 2B. Okay, so that's the rule that told me that that is correct. Let's look at the second one. How many sig figs there? Let's put it in the chat. I agree with the students that put 6 sig figs. Okay. Why is that value 6 sig figs? Rule 1B and rule 1C. Okay. Rule 1B tells me that the 0 between the 5 and the 6 is significant. Rule 1C tells me that the 0 after the 7 is also significant. Okay. Excellent. Yes, the 0 at the end. How many sig figs in the third digit? Great job. 5. The rule that tells me that that is true is rule 1C. What about the fourth digit? How many sig figs there? Excellent. This has 6 sig figs. And again, rule 1C. What about the fifth digit? Excellent job. There's 2 sig figs here. The rule that tells me that this is 2 sig figs is going to be rule 2B. Lastly, how many sig figs on the last one? Excellent job. You guys are getting this. So proud of you guys. This is because of rule 1C. There are more practice problems than this on the in-class worksheet. Remember that I will be posting the answer key for the in-class worksheet later this week, so you can just do that work and then see if you got them correct. Any questions? When you have a measured number, how do we determine the number of significant figures? Again, the numbers that carry meaning in that measured value. Any questions? Great. Since there are no questions, let's move on to the next concept. which is scientific notation. As I mentioned to you guys a few moments ago, when it comes to scientific notation, this specifically is going to be a method that we utilize in science to express very large numbers or very small numbers. And this all has to do with scientific measurements. So we are going to utilize this notation so everybody in the scientific community knows if we're talking about a very large number or a very small number. So to give you guys an example of a very large number, here you can see that we have the diameter of planet Earth, and this is a super large number. As you can see, this is 12,756,000 meters, okay? An example of a very small number is going to be the mass of one virus particle. In other words, the mass of one virion particle. As you can see, this has a lot of zeros. This is way less than a gram. So you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 14 zeros. Nobody got time to write all those zeros. So through scientific notation, we can actually have a way in we can write these numbers, and then we understand if we have a very large number or a very small number. Now, scientific notation is actually a concept that in our textbook is discussed in chapter 1. So when you're finding practice problems for scientific notation, please refer to the ones that I assigned from chapter 1. So let's now learn how to write in scientific notation. So when we're writing in scientific notation, understand that there's rules. Give me one moment. There's going to be rules when we're dealing with a very large number or when we are dealing with small numbers, okay? So when it comes to this, understand that specifically, when we have a large number, we need to write, if it's not there, okay, the decimal place that is implied. Okay, so for the value that we have here, our implied decimal place, but it is here, is going to be after the last zero. And then the rules for writing things when it comes to scientific notation, as you can see in step 1, we're going to move that decimal place to obtain a coefficient that is at least 1, but less than 10. Okay, so as you can see in the notes here, we're going to move that decimal place from right to left 1, 2, 3 times. That's where the 3 places come in handy. Okay, because remember, your coefficient needs to be at least 1, but less than 10. So that's why our coefficient turns into 2.4. Okay. Now, where do we express that we move that decimal place from right to left 3 places? At the level of the exponent. Because if we are moving from right to left, okay, our exponent is going to be positive. And it's going to express the number of places that we moved. So we moved 3 places. This is why the exponent is 3. And it is a positive value. So every time we're writing in scientific notation, again, we determine the coefficient times 10. And then the exponent in that coefficient is going to be the number of places that we moved, and it may be positive or negative. In the case of having a large number being converted to scientific notation, we have a positive exponent. Now, what happens when we have a small number? Well, in the case of a small number, we have a decimal place that is written. Again, we are going to move it such that we create a coefficient that is at least 1, but less than 10. So we're going to move it 1 time, 2 times, 3 times, 4 times. So now our decimal place lives here. This is where the 8.6 comes from. Now notice that we move that decimal place from left to right. And since we did it left to right, then that means that our exponent is going to be negative. But again, the value is going to be how many places we moved that decimal place. And since we moved it 4 places, that's where the 4 comes from. One last thing that we need to remember. If you're giving a measured value and you need to convert it to scientific notation, you need to keep the same number of sig figs, okay? So we just learned about sig figs. So in the value 2,400, there are 2 sig figs. So that means that my coefficient needs to be 2 sig figs. In the value 0.00086, that has also 2 sig figs. So when I convert it to scientific notation, my coefficient, because we know that in scientific notation, the coefficient is what carries the number of sig figs, it also needs to be 2 sig figs, okay? Let's practice taking some measurements and converting them into scientific notation. So as you can see, this is problem 2 in the in-class worksheet, okay? So I'm going to do A and B, and then we're going to do as a group C through F. So we have the following measurement. Now, let's put an R for right or L for left. Which way am I going to move the decimal place? Towards the right or towards the left? Excellent. I need to move it to the right. So I'm going to move it 1, 2, 3, 4, 5, 6. Okay, so I know that that's going to be my exponent. Great job, Victoria. Yes, I'm glad to see that you get this concept. So this measurement has 3 sig figs, so my coefficient needs to have 3 sig figs, 1.85. Then I write times 10 because I moved from left to right. My exponent is going to be negative. I moved 6 times. I write my unit. Okay, let's look at letter B. Okay, again, using R or L. Which way am I going to move that decimal place? Towards the right or towards the left? Remember that the goal of moving that decimal place is to create a coefficient at least 1 or less than 10. Excellent, towards the left. So I have this decimal place here. I'm going to move it here, okay? Now, this is where sometimes students, don't pay close attention to these transitions, okay? How many sig figs is in the measurement 60.0 seconds? How many sig figs? Excellent. So if this has 3 sig figs, your coefficient must have 3 sig figs, because remember, the sig figs carry meaning to your measurement. You cannot just start dropping numbers or digits just because you feel like it. They carry meaning in a measurement, okay? So understand, if you do that in other classes, please don't use those practices here, because those are not the rules that I'm presenting to you guys. So my coefficient needs to be 3 sig figs. So 6.00 is my coefficient. If you write a coefficient of 6 by itself, it's not correct, because you started with 3 sig figs, your coefficient needs to have 3 sig figs. Then we do times 10. We move that decimal place from right to left. That means that our exponent is positive, and it's going to be a 1. And we need to write that 1. And then we write the unit. Seconds, okay? So we have 4 more problems. Let's look at problem C together. Great job. Excellent, Victoria. It stays the same. I'm glad to see that some people got ahead. They already know this semester, you know, if you get ahead, you know, it's always good because then you can reinforce those concepts here in class. So when it comes to 6.7, 6.7 already is a value that fits the rule of at least 1 and less than 10. So we are going to write it 6.7. To express this in scientific notation, we're going to do times 10 to the 0. Why? Because we didn't move the decimal place anywhere, and 10 to the 0 equals 1. Okay? And then we put the unit of grams. So at this time, I want you guys to take a minute and write the answers for D, E, and F. I'm going to give you guys a minute. Thank you for the answers in the chat. Let's actually write them here in detail, just for any student that needs the extra notes, but great job. Excellent. Thank you, guys. Great job. So for the first one, we're going to move our decimal place 1, 2, 3, 4 places from left to right. So we're going to do 5.010 times 10 to the negative 4 milligrams. Because remember, here, the 5, the 0, the 1, and the 0, they're all significant. Okay? Next one. We're going to move this 1, 2 times. So we moved it in this direction, 2 places. So this is 4.500 times 10 to the 2 seconds. And then lastly, we're not moving anything on letter F. So we have 3.85 times 10 to the 0 grams. Okay. Any questions on how to convert a number into scientific notation? Excellent. Put a 1 in the chat if you're ready for the next concept. Awesome. Great. So the next concept that we're going to talk about is rounding. I always find that this is the one skill that sometimes students forget. And if you don't say round, then all of a sudden students are like, oh, but you didn't write round. Rounding is always implied when we are doing arithmetic problems. So when we're adding, subtracting, we're always rounding. So understand that rounding, even though you will see in exams and chapter quizzes and everything, it says express your answer in the correct number of sig figs. Rounding is implied. Don't forget to round, okay? So understand that when we are rounding, you're basically going to underline the digit, okay, that is next to the value that you're focusing in. And if it's 5 or greater, you add one more. If it's 5 or less, you leave it as it is, okay? And everything after that is a 0. Now, understand that in chemistry, it depends, okay? Because everything is a 0. Remember that. Keep in mind the sig figs. Okay, so please don't drop everything and make it a 0. It depends on the instructions that you're given. So I'm going to do the first one with you guys, and then the other ones we're going to do as a group in the chat. So we look at the first statement. It says round to 3 significant figures, the measurement 10.253. Okay, so I'm going to read my digits from left to right. My 3 significant figures are going to be these 3. Okay, so what that means is that when I'm looking next door, I'm looking at this 5. Okay, so the rule says that if it's 5 or greater, we add one more. So when we round this value to 3 sig figs, we're going to do 10.3 meters. Okay. Let's go through the second example. Round to 1 significant figure, 25.01 kilograms. Okay. So what is my 1 sig fig here? The 2. So when I look at this, I look at the 5 next door. Again, if it's 5 or greater, add one more. So if I try to round this to 1 sig fig, my answer is 30. Because remember that 0 after the 3 is a placeholder. Let's learn in this class that we are not going to be extra. I'm going to show Dr. Luz that I know some more. If I put a decimal place after the 0, why is that not correct? Why is writing that extra decimal place not good? Thank you, Francisco, because it makes it 2 sig figs. Excellent. Thank you, Divya. Exactly. Thank you, Victoria. Exactly. It makes 2 sig figs. So let's not do that, you guys, because I know sometimes students just get too excited and they're like, oh, these little mistakes. You guys, you don't want to miss those points with those little mistakes, okay? Now, let's go through the third and the fourth. So 3 sig figs. What's going to be the answer of that? Oh, somebody already got there. Awesome. So what is the answer for the third one? When we round it. Great job. What about the last one? When we round it to 2 sig figs. Excellent.
I have a quick question.
Go ahead, Kayla.
How do you know like which one you're underlining?
Because it's going to be the one after you highlight. So for example, I have 3 sig figs, right? If I read this value from left to right, sig fig number 1, sig fig number 2, sig fig number 3. So then I look at the 7. If I look
Gotcha.
at the last one, we need to round it to 2 sig figs. So when it comes to this, I will say, okay, I need 2 sig figs. So this is the first one, this is the second one. The one next door to the second one, that's the one that I'm looking at.
Okay, thank you.
No problem. Any other questions in rounding?
Yes,
Go ahead, Ms. Victoria.
thank you. Do you always have to put the underline under the estimated? Under the one that, then the digit that's being rounded up or down?
Not really. This is just a
Oh, okay.
practice, just because
Okay.
since I'm introducing this concept, and I know that some students here have background, but other students don't have background. So I'm trying to serve everybody, from the people that look at these values and they know the answers right away, to the students that are like, I don't know how she got that. So that's why I do all the markings possible to serve all of you guys.
Okay, so that means it's not a repeating number like in other contexts. Sometimes that underline has another meaning.
Yeah, no, in here. I'm
Okay,
just
thank
trying
you.
to make you guys pay attention to what I'm looking at when I'm doing things like this.
Thank you very much.
No problem. Any other questions in rounding? Great. So let's understand that we already know how to measure things. We already know how to write measurements. We already know how to convert them into scientific notation. We know how to determine the digits that carry meaning. We know how to round them. So now we're going to learn, how do we deal with measurements when we need to do mathematical operations? So that takes us to the concept of, when we have significant figures, meaning I have a measurement, but then I have to do mathematical operations on it, how do I deal with those numbers? Well, we need to set rules for addition and subtraction, and we need to set rules for multiplication and division. Let's start with the addition and subtraction. So this is the reality. In addition or subtraction, the final answer is written, so it has the same number of decimal places as the measurement with the fewest decimal places. And understand that when it comes to fewest decimal places, it can be no decimal places. That's where I find that some students have, troublesome with this concept. If you have a digit in your series of numbers that you're doing addition or subtraction, and it doesn't have any decimal places, then understand that's the least number of decimal places, having none. So here we have an example of addition. We have 3 different measured values. The first one has 3 decimal places. So understand that decimal places, my shorthand for it is DP. The second value has 2 decimal places. The last value has 1 decimal place. So all of these values, as they are, we are going to add them and put them in the calculator. As you can see, calculators, okay, don't have the concept of sig figs. Calculators, you plug in numbers, is going to give you a calculator display, okay? So it is important that you know that your calculator display is not your final answer, especially because when we're discussing this concept, you need to, as I mentioned to you guys, remember that rounding is not something that I'm going to say at times. It is implied. You need to round, okay? So your calculator display, by taking these 3 measure values and adding them, tells you that the result is 66.102. Now, based on your sig fig rules, you will say, oh, wait, the fewest decimal places in this case is going to be 1 decimal place. So that means that my calculator display needs to be rounded to 1 decimal place. Okay, so similar to the question that was just asked, when it comes to this, you're going to say, oh wait, these numbers I need to keep because that's to the first decimal place. So then I look next door to the first decimal place, and as you can see, it is a 0. So a 0 is not going to add to the 1. So what I'm going to do to round it is just drop those last 2 digits. This is what I mean. Don't turn those zeros into zeros, because remember, if you write 66.100, this is 5 sig figs, and that is not correct. Okay, that is not the rule. So understand that this is not correct. So pay attention when you're doing rounding. So my final answer is going to be 66.1. Now, we also have rules for when we're doing multiplication and division. Okay, and in multiplication and division, you can see that the rule is the final answer is written such so that it has the same number of sig figs as the measurement that has the fewest sig figs. Okay, so here we have an example of a multiplication. We have 24.66 centimeters multiplied by 0.035 centimeters. Okay, when you take those two measure values and you put them in your calculator, you see that your calculator display is 8.631, but that is not your final answer, because when we pay close attention to this, you can see that this has 4 sig figs, this has 2 sig figs. Okay, so even though that's my calculator display, okay, I need to take this calculator display and round it to 2 significant figures. Okay, so when I'm paying close attention to my digits, I'll say, oh, these are the first 2 significant figures. Let me look at the value next door to the 6. It is a 3. Because that 3 is not adding to the 6, then I'm going to write as my final answer 8.6. In terms of the units, this is centimeters squared, okay? But it's going to include this 2 sig figs, okay? Any questions when it comes to multiplication and division or addition and subtraction? Then let's do some practice. I want you guys right now to take a moment and do 1 through 4. Let's do 1 through 4. As a side note, make sure that you print or you have in handy a periodic table for this week, because we are going to utilize it in class. So there's a periodic table for you guys on Canvas, but I need you guys to have a periodic table. We only have 3 minutes left. What is the calculator display for number 1? Let's put it in the chat. Calculator display for number 1. Excellent job. 61.87. But then if we apply the sig fig rule, what's going to be our final answer? Excellent job. Menos 87.51. What is the calculator display for number 2? Excellent. That's what I got also. Based on the sig fig rules, I see that there's different answers. So the first measurement has 3 decimal places. The second one has 4 decimal places. So we need to round this answer to 3 decimal places. Excellent. So it's going to be negative 86.176. Okay, for the students that gave me only 2 decimal places, remember the rules. Three decimal places is the smallest number of decimal places here. Let's do number 3. Let me see, what is the calculator display? Excellent, that's exactly what I got also. 25.50. Okay, first value has 2 sig figs, the second value has 4 sig figs. Great job. The answer is 26. Last one, we're going to divide those 2 numbers. Yeah, there's a whole bunch of numbers there. 0.590257649. Okay. And then we need to round it. Excellent, to 3 sig figs. 0.5903. Okay. Remember the rules for sig figs. Don't be dropping numbers just like that. So tomorrow in class, we are going to go over problems 5 and 6, which is when we have multiple operations in our equation, how do we deal with sig figs? So that's all for today. Thank you guys for coming and welcome to Chemistry 104. Have a great day, you guys.
Thank you.
Bye, thank you.